Alright, today we're going to work through the following conceptual questions in the Newton's Laws of Motion section. So let's start with number 1. The question reads, according to legend, a horse learned Newton's laws. When the horse was told to pull a cart, it refused, saying that if it pulled the cart forward, according to Newton's third law, there would be an equal force backwards. Thus, there would be balanced forces, and according to Newton's second law, the cart wouldn't accelerate. How do you reason with the horse? The answer lies in that the horse fundamentally misunderstands Newton's second law and Newton's third law. So let's draw a picture, all right? So here we've got the horse. It has legs, has a head, it is a horse. And here we have the cart. Now, I don't know exactly how much the cart is going to weigh, so let's say that it exerts a force of 400 newtons. Actually, pardon me. Let us say, briefly, that the horse, when it begins to pull forward, exerts a force of 400 newtons forward. Now the horse argues that because it is exerting a force of 400 newtons forward, that the cart will also be exerting a force of 400 newtons backward on the horse. And so, because these two forces are balanced, the cart will not move. Now, I've drawn the force for the cart in red and the force for the horse in black, because it's important to see where these forces are coming from. Now let's go to Newton's second law. Alright, because the horse is working off of Newton's third law, which states that for every action there's an equal and opposite reaction. Newton's second law, though, explains how an object will change velocity if it's pushed or pulled. So, first, the law states that if you place a force on an object, like the horse is placing a force on the cart, it will accelerate, and it will change its velocity in the direction of the force. So, yes, the cart is exerting a force of 400 newtons back on the horse. Yes, there is a balanced pair of forces here. But, because of the second law of motion, the cart will begin to move forward because the force is being applied in that direction. And the cart, when the force is applied to it, is going to accelerate in the direction that that force is being applied. Alright? So now, once the cart begins to roll, then Newton's first law acts on it, so it begins to conserve its momentum. And it just continues moving as the horse continues to exert pressure on it. So that's how you reason with the horse. So that's Newton's second law and Newton's first law sort of collaborating together to prove to the horse that in fact you can move a cart. Now that we've gotten that out of the way, let's go to the second question. So it asks us about accelerometers. And it says, an accelerometer is a device that measures acceleration. A basic accelerometer is nothing more than a jar filled with water and a cork suspended in the water. When the jar is moved, when the jar is moved, the cork points in the direction of the acceleration. How does this type of accelerometer work? So first, let's sketch the accelerometer, and we're going to use 3 different colors here. All right. So first, we've got the jar. Now, the water, which will be green, be the green line there. I don't know actually if you can see that. So never mind. We're just going to use black. Come to think of it, the black will also be water. All right. You can see that. Now, finally, the cork, which is red. And now, that's about where the water is passing on that cork. Okay, so now the question says that this device is an accelerometer because if we move it, let's say we move it this way, the cork will point in the direction of that acceleration. So it will point this way. Why is that the case? Problem asks us. Let's look at the first law. Okay? So Newton's first law of motion states that an object will always act to preserve its current state in terms of motion, in terms of acceleration, in terms of momentum. Specifically, it says that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. So if we leave this accelerometer right here, the cork's not going to move unless we put a force on it, in accordance with Newton's first law. All right. Now the cork weighs, let's say it weighs however much it weighs. I don't know. We'll make up a mass for the cork, actually. The mass will be 5 kilograms. All right. Now, if you remember, every object that has mass has also what is called inertia. And inertia is the quality of an object that makes it resistant to changes in its movement state. Okay? So the cork has a mass of 5 kilograms, which is an insanely heavy cork, but whatever. Cork has a mass of 5 kilograms, and so therefore its inertia is also 5 kilograms. It is resistant to being moved. All right? Now let's say that the water has an inertia of 25 kilograms. It makes sense that the inertia of the water is going to be more than the inertia of the cork, because an entire jar full of water weighs more, is more dense than is the cork. All right? So the water has more inertia than does the cork. So now, if we move this jar this way, in accordance with the problem, the cork and the water naturally want to act so that they stay where they are because of Newton's first law. An object will remain at rest unless a force is acted upon it. And furthermore, inertia, which is the principle of which is the resistance of a physical object to a change in its state of motion, will cause the cork and the water to try and remain at rest as long as they can. So, let's move this jar again. Okay? So now the top of this cork is surrounded by air, which has very little inertial value. Okay? Or value in terms of inertia. So this top part of the cork will want to stay put. But also, the amount of movement that we're putting into the jar probably will overwhelm its inertia. Okay? So this part of the cork will want to move. And it will specifically want to move this way in accordance with Newton's second law. We're applying a force, so this cork wants to accelerate in the direction of that force. It wants to go this way. All right? So now let's look at the bottom part of the cork. The bottom part of the cork is put in water. And water has higher value in terms of inertia than does the air. So the water is more resistant to movement than is the air. All right? Now what that means in this problem is that the top part of that cork only has very, very little resistance to it moving forward in accordance with Newton's second law. This part of the cork does have a problem moving forward in terms of Newton's second law. Why does it have a problem? It has a problem because the water, which has a higher value of inertia, wants to stay where it is and so pushes back on that cork. So ultimately what happens when you move this accelerometer is the top side of the cork, it'll be represented by this, because we'll see what happens to the cork. It wants to move, okay? So the top side of the cork has moved from here to here, all right? Now the bottom side of the cork will also move a little bit. But remember, the inertia value of the water is greater than the inertia value of the air, so it's not going to move as far. It's going to move maybe here, all right? So now, if this side only moves a millimeter and this side moves an inch, what's going to happen to the cork? The answer is the cork is going to tilt in the water. All right? So now, instead of the cork being straight up and down, as it was, it is leaning towards the direction of the acceleration, because this part of the cork wants to stay put because the water is exerting pressure back on it when it tries to move, because the water is also resistant to movement. This side of the cork wants to stay put, but the movement is forcing it to go that way, and the air is offering pretty much no inertia resistance to it moving. So that is why when you move the accelerometer, the cork will point in the direction of the acceleration. All right? Now let's briefly do the third and fourth problems, and we'll finish this up. So the third problem asks us to make a diagram of the forces acting on a submarine. All right? The submarine is submerged 50 meters below sea level, and we're supposed to draw all of the action-reaction pairs on it. All right, so here's our submarine, and here is the seafloor, and here's the water, the surface of the ocean, I'm sorry. So it's 50 meters below the water. Now, think about this. The submarine is staying put, right? So it's not rising, it's not sinking, it's sitting here equally. So that tells you that the amount of force the submarine is exerting has to be equal to the amount of force the water is putting down. Let me put it another way. So we know that all of this water, all of this 50 meters full of water is pushing down on the submarine. The submarine is being pushed toward the bottom of the ocean. But the submarine is full of air, it has ballast tanks, and the buoyancy of those ballast tanks here is equal to the force being exerted downward on the water. That's why it's not moving anywhere. If this force, the force of the ballast tanks, were more, then the submarine would rise. If it were less than the amount of water being exerted, or the amount of force being exerted by the weight of the water, then the submarine would sink. But because it's just sort of sitting there, the forces are imbalanced there. So the water pushes down on the submarine pushes up on the water. Now this next one is the harder one to understand. Okay? So here is the bottom of the ocean, and therefore the world. All right? This is the Earth. Now, obviously, gravity is still acting on the submarine, even though it's in water. All right? So gravity's pulling this submarine down to the Earth. All right? Into the center of the planet. But the submarine is not moving. Why? Well, we've already discussed how its buoyancy is keeping it in place in the water. But here's the other thing. In addition to the submarine being acted upon by the force of gravity pulling it downwards, the submarine also pulls the world upwards at the same force. All right? So remember, gravity is the attraction between two objects, not between one object and another. It's the attraction between two objects. So if there's gravity acting on the submarine, on the part of the Earth, there's also gravity acting on the Earth on the part of the submarine. Okay? So when the Earth pulls the submarine down, the submarine also pulls the Earth up. Now you may ask, why doesn't the submarine pull the Earth up then? Why when we drop an object, does it fall instead of pulling the Earth up to meet it as well? Well, the answer lies in the fact that the Earth is almost infinitely more massive than this marker is. So this marker has very little inertia compared to the Earth. The Earth isn't going to move out of place to move up to the marker, because the marker is exerting a very, very tiny force on a very massive body. By contrast, the Earth, which is extremely massive, is exerting a lot of force on something that has very, very little inertia, that is to say, the marker. So there's the diagram of the forces involved in the submarine problem. Finally, let's talk about the difference between mass, inertia, and weight. All right. So we tend to treat mass and mass and weight as pretty much the same thing. It's not. All right. You may have heard that if you weigh 100 pounds on Earth, you'll weigh 80 pounds on Mars because it is smaller, right? Or 500 pounds on Jupiter. All right, that's weight. Weight is a function, or weight expresses how much force, with how much force you are being pulled into the center of this planet. All right. So weight is a vector. All right. It expresses not only a magnitude 100 pounds, but also a motion towards the center of the Earth. Okay? Now, by contrast, mass is not a vector. Mass is just a value. It just gives us how much of something there is, and it's hard to explain exactly what mass is without using the word mass again. But if you think about it, mass is just how much of an object there is. It's sort of difficult to explain in and of itself, but remember, weight is with what force an object is being pulled to the center of the Earth in accordance with gravity. Mass is how much of something there is. Now, inertia has the same value as mass, and inertia is just, as we've discussed before, how resistant to a change in motion something is. So, with that, we finished up all 4 of the problems in Newton's laws of motion, and good luck.